for the lecture to begin.
I can't pause you.
Quick reminder to everyone, there are voice isolation locations at the back of the lecture hall. If you need to discuss things, please do it there. For the people joining us on the YouTube stream, we are DGen Tech Incorporated. We are a group of furries in the science, technology to begin, engineering, medical, and quick reminder to everyone. There are voice isolation locations at the back of the present our very own Physwolf, who will be giving us a brief look at optical imaging modalities. For the people joining us, Physwolf will be covering some introductory topics regarding modern optical imaging modalities. The talk will center around essential fundamentals and explore some of the vast plethora of imaging techniques which have come out of the last few decades of research. The talk is to be presented at an introductory level, but Physwolf is a world expert in some of these topics, so feel free to engage him in in-depth questions and commentary. Thank you. Physwolf, take it away.
Perfect. Can everyone hear me?
Yeah.
Okay, yeah. Okay.
Yes.
Cool. Oh, I need to switch this thing over to, there you go. All right, well, hello, I'm Physwolf, and yeah, thank you for the introduction, DT. So let's just hop right into it. Okay, so what is this talk? So this talk is really meant to be kind of like just a very high level kind of introduction to a bunch of things that I certainly find interesting in optical imaging. A good portion of this focuses on microscopy techniques, just because that's where a lot of the interesting stuff happens, or has happened in the last couple decades. But this is really meant to just be like a primer. So, like, if you see something that's interesting or so on, make sure you ask questions, bother me after the lecture, et cetera, et cetera. We're not going to go into anything super in depth, but we certainly can in follow-ups and questions and so on. Very briefly about myself, I'm Physwolf, the Canadian physics wolf. I have a background in a lot of biomedical optics. So like I did, for example, my PhD in biomedical engineering, studying novel absorption microscopy techniques that we'll very briefly touch on as part of this talk. I have worked at 2 startups now, both my current role and a previous role. Also heavily involved with optics, and I've worked in my career already from everything from like 200 nanometer UV up to 2500 IR, and designing systems, optics, sensors, everything in between. So I've touched quite a wide range of things in amongst that time. So let's start with the basics. We got to define some things here. What is optical imaging? I'm going to be very, very high level with this. I'm going to say it deals with EM radiation, generally in the UV to IR, though those ranges are also not very well defined. But realistically, I would say optics are anything that we're going to do with standard things that look like optics, lenses, mirrors, these kind of things. And realistically, that extends really far into UV. You know, if you look at some of the like EUV stuff that's being done in modern lithography, all the way up to, man, very, 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 very long wave IR. You start getting to crazy materials that don't even feel like they should be, working for lenses and so on. So we're going to talk about stuff that deals with that kind of electromagnetic range. And imaging, the other part of this word, what does imaging mean? Imaging usually refers to this kind of specific optic term where you're re-imaging two conjugates. And so you've probably all seen this in like an introductory optics course where you have, one image and it goes to another image. Those are called conjugates. And you're re-imaging the conjugates. Like, you also have a conjugate off infinity, right? Like if you're doing like astronomy or something like that. And yeah, like generally when you're building these things, you're building these out of big optic systems. You're talking about things like optic rays and so on, which we'll define a little bit in there. But like kind of going back to like this seems like a really introductory diagram, but this is actually what you do when you're doing optical engineering. Just a much higher level version of it, and using a lot of nice software to make this a little bit less painful. As you're making these kind of big lens stacks up. Okay, so how do we want to think about light? So you've all heard the classic, like the rays, waves, particle kind of thing, and they're all really useful in different things. There are different aspects. Really, light's just an EM wave, right? But it's really convenient to kind of abstract out this wave, and it's a little bit more palatable. And we can do this, for example, if we take like ISO fronts, like ISO phase fronts, and we can draw those out as kind of these lines that are perpendicular to the direction of travel, right? We call those wave fronts. Those are really handy for kind of capturing what is the shape of these kind of EM structures. And then we'll define these things that are perpendicular to those wave fronts called rays. Rays are really nice because they kind of follow this hyper-idealized, light travels in a straight line type formalism, which is extremely not true, but very accurate for like 99% of cases. But it's really useful for designing optics and talking about some really high level kind of concepts. Sometimes, though, you do have to go back to the fact that these are particles. Realistically, these are photons, and especially when you're going into something called turbid media. So turbid media is something that's going to cause a lot of scattering to those wavefronts. So at a certain point, you imagine you have this nice coherent wavefront. It starts to interact with a highly scattering media. It's going to break up, and now you're best described by just kind of single photon interaction by something called a radiative transfer equation, which is awful. We'll look at it later. And you generally have two kind of regions here. You have your ballistic region, which is where everything behaves like you want it to. You have a kind of a quasi-ballistic region where you're scattering, but you're still getting a lot of forward scatter. So as long as you don't care about maintaining this kind of perfect ideal waveform, you have like pseudo perfect waveforms still. And a lot of biomedical optics operates in this kind of quasi-ballistic range where you sort of maintain this kind of coherent propagation. And then beyond that, you go just into the diffuse regime. And in the diffuse regime, there's actually still a bunch of optic imaging techniques that work down there, despite the fact that you've completely lost any kind of spatial coherence or temporal coherence to your light at that point. And it's really interesting to remember that a lot of these things like this what is turbid media, it really depends on the wavelength you're talking about. And I think a classic example is if you wanted to look through like clouds, either clouds on Earth or dust clouds when you're doing astronomy. Your choice of wavelength really matters, right? What looks like a highly scattering media to one wavelength is not necessarily scattering or very scattering to another wavelength. You can kind of play around with this a bit. And this kind of represents sort of the general spectrum that you're dealing with in optical imaging. Everything from extremely coherent techniques like confocal microscopy down to techniques that can operate in this diffuse regime like photoacoustic tomography or diffuse optical tomography or these kind of things. And if you go further and you kind of look at, especially in like biology where you're almost always limited by transport in tissue, you get this kind of fancy thing that everyone likes to reprint on their papers, where basically if you kind of almost have this linear relationship between how far you can penetrate into some turbid media and what type of resolution you're going to be able to extract. Keep in mind that resolution, that's kind of related back to how coherent you're maintaining this wavefront. Okay, so that's a lot. So what kind of properties do we care about in light in general? Well, we have the color, which measures the wavelength, wavelength there. And there's lots of things that have pretty extreme wavelength dependence. Like the glass that you use, for example, will usually have dispersion. This is generally just when I use the term dispersion, this just means wavelength dependent properties. It's generally referring to wavelength dependent propagation, right? So if you have like a refractive index of a glass, like a really common borosilicate glass, MBK7, you have a non-constant refractive index. This is what gives you chromatic aberrations. This is also, for example, what stretches your pulses. If you go in with a super short femtosecond pulse, this is the effect that's gonna stretch that out for you. We also have wavelength dependent absorption. So a good classic example from biomedical imaging is the difference between oxy and deoxyhemoglobin. I don't know if y'all remember like the like phase with smartphones from a couple years ago, where you had like that little sensor you could put your finger on there, and it would shine a bright red light into there, and it could tell you your blood oxygen saturation. It's just using this curve right here. It's just looking at the amount of light that gets scattered back off two LEDs, and just basically doing like solving a very simple linear problem to get back at the relative oxygenation. You also have wavelength dependent scatter, and you'll also have wavelength dependent transmission, right? Like here's just a selection of glass, for example, from Thorlab's catalog, and the types of wavelength ranges that you can even use things at. Like if you're stuck down in UV, you're basically with UV fused silica and calcium fluoride. If you want to go out to hundreds of microns, you're starting to use things like Teflon, right? That doesn't even feel like that should be a lens, right? But different wavelengths are different. Different things are different. We also care about coherence. And sometimes we don't just want good coherence sometimes. Sometimes we want kind of bad coherence. And a classic example of this is optical coherence tomography, OCT, which actually uses low coherence interferometry. I'd love to talk about in length. That's like its own thing altogether. And of course, sometimes you want long coherence interferometry, like the classic LIGO doing some gravity detection there. And I can't remember the coherence length that they're working on here. I feel like it's in like the hundreds of kilometers or something, absolutely insane. Versus like an OCT that's working at 20, 30 micron coherence length. You care about sort of the quality of the wavefront. So, for example, remember we had all those nice kind of perpendicular structures going along there. If all these don't line up at a focus, for example, we generally call that aberrations, right? We want to avoid picking up these aberrations as we're going through our system, if you care about forming a nice image in general. So there's this whole aspect. We care about the temporal properties of the light. So if you're in a short pulse regime, like a femtosecond, picosecond regime, you have to keep your short pulses together, which also introduces a temporal beam quality. So you can imagine even back here, right? I have some rays that aren't quite hitting the focus at the same time. Now you can imagine I also care about the path length, the phase path length of that. If I'm trying to focus like a 5 femtosecond pulse, I need to make sure that all of those components of my 5 femtosecond pulse reach the focus at the same time. That's actually extremely non-trivial. We care about polarization. Polarization is, just is the actual direction that the electric field is I'm spacing on this term. I'm going to say traveling. It's not traveling. It's oriented. There, we'll say oriented. The direction of the electric field is oriented. There's a bunch of microscopy techniques that will detect how polarization states interact with the material, and you can get contrast from that, because now you can directly see how good of a wave plate that material acts as, and use that as an imaging contrast. That gets really cool. You can also use this pretty extensively just in sort of your optic piping, as it were, to get good directionality control. You get nonlinearities. Literally everything is nonlinear. It's just a matter of how much. So you get all different kinds of wavelength mixing, different kinds of nonlinear scattering that you can take advantage of to get contrast. And here's just like a short list. What kind of contrast can we even get? So contrast, remember, if you want to think of your imaging system as kind of like a black box, in general, we're pumping in something, usually light, not always light. We interacts with our system under test. It's going to give us out contrast, right? Some things are going to interact with the material differently than it'll interact with other parts of the material, and that's how we'll get contrast back. And you can get all kinds of things, scattering, transmission, different sort of confocal focusing behaviors, multiphoton absorption, super resolution techniques. You can take advantage of this. We're going to go into these in more detail. Different kind of nonlinear scattering, like Raman techniques. You can take advantage of absorption harmonics, holography, which I won't touch here because it's black magic and I don't believe it's real. No, I just don't actually know it that well. Okay, so let's start. That's kind of like the primer. Incoherent imaging. So incoherent imaging, this is what everyone's aware of. This isn't anything new. We're just starting from something easy. Incoherent imaging, we're taking just an incoherent piece of light. Usually we're going to bounce it off something and we're going to form an image. You would actually find it was actually kind of hard finding a good reflection mode image of a microscope like this, surprisingly, on Google. But imagine just like a normal microscope, we're lighting it up from the top, light bounces off, we see it. Beautiful, it's easy. You can also send the light in from the other side. You can transmit light through something. This has also been done forever. Imagine you have a big bright light below the sample, and then you're feeding the light up and you're looking at the light that transmits through. This is really nice for looking at things that have kind of subtle structure to them, that have different absorption properties. Like, for example, these green parts here are absorbing light differently than the white parts here, giving you an extra contrast there. Very nice. You can also add dyes. So this is probably, I would argue, this is probably the most impactful use of microscopy in biomedical imaging probably ever, which is doing histology imaging. So anytime you want to look at a piece of tissue, you take it out of the thing that you care about or don't care about. You embed it in paraffin wax, you slice it, and you end up with something that looks kind of like this, but imagine there was no color. Imagine this green wasn't here. And then you say, oh, I'm going to add some dyes that specifically bind to the thing I'm trying to look at. And like, for example, here we have hematoxylin and eosin stains that bind to positive and negatively charged regions in the tissue. And they'll highlight things like DNA, for example. So like all the nuclei will highlight as these kind of like dark circles. They'll show all the surrounding collagen as this kind of pink color, et cetera, et cetera. And this has been absolutely invaluable. This is also a 100-year-old technique, but it just felt like mentioning it. We're talking about transmitted microscopy. You can also use something called dark field transmission. This is where it gets kind of cool, where you use like an off-axis illumination. So instead of illuminating with a big bright light, a bright field transmission behind your sample, you image with a big bright light, but you block the portion of the light that wants to make it into the microscope. And so what you see is anywhere where the light is not interacting with the sample, you just get darkness because the light misses you. And then anywhere where the sample interacts with the light, it gets deflected. And maybe it gets deflected into your detection system. This is really, 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 really powerful from a dynamic range standpoint. You can imagine if I'm trying to image something very small and very poor contrast, like a bubble. Like I want to image like a 5-micron bubble or something like that. If I try to do this with a regular bright field microscope, I have to play this game of dynamic range where I have to tell the difference between my bright white background and this slightly off-white region that might be below my resolution. It might be very difficult to detect, as opposed to a dark field microscope setup. Now I need to tell the difference between a black background or a noise floor and something that's not my noise floor. So dark fields are insanely useful for picking up these kind of very subtle structures. Very much related to dark field imaging, which is just also cool, is Schlerin imaging. Schlerin imaging, there's a bunch of different ways of doing this, but it's kind of the same idea where you set up an optic system so that any slight perturbation to the pathway will mean that those light rays will either hit or miss your detector, right? And you can the classic kind of thing is you've probably all seen these kind of videos where you sort of have like a gray, like a neutral background, and for example, like some heat or some kind of disturbance will go into the air, and you'll pick up these brighter and darker spots, right? So this is really, really powerful for finding these small, subtle differences in something that might otherwise be extremely difficult to detect, right? Like here you're detecting very, very, very fine perturbations to the refractive index that would basically just wouldn't see that on a regular camera at all, right? Also, I have no idea how they took this image. I just think it's really cool. Usually for Schlieren imaging, you have to have very precise control over your illumination and your receive. So I don't know what kind of magic they're doing this. Maybe the sun's behind these things or something. But I don't know. It's really cool, and I actually really want to know how they did that. Confocal imaging. We're still on like 100-year-old technology here, but we're getting there. What do I mean by confocal? So 2 foci are better than 1. Back here, you can imagine for all these images, all these imaging systems, we have kind of an incoherent source, and then we're focusing light coming into our camera sensor or our lens or our eyepiece or something like that. Now what we're going to do is we're going to send out coherent light. I'm going to focus my light to a spot and then only look at the light coming back from that spot. So we get 2 focuses overlapping, confocal, amazing. And this gets you a much better point spread function. The point spread function is the impulse response of the system. Does anyone know what the concept of like impulse response or linear shift invariant systems? Seeing some hands. So basically your point spread function, if you were to image an infinitely small spot with your system, this is what it would look like. It would look like your point spread function. And in general, if you're operating in a linear shift invariant system, which that's a good approximation for a lot of these systems, anything you image will just be the convolution of your point spread function. That's actually a really nice way of modeling systems and simulating systems. So the better point spread function I can get, the better resolution I can get on my hardware. Confocal systems, 2 focuses, right? You have a light source that usually you have, if you're doing that, you can do this with like an incoherent source. You can still do this with an incoherent source, like an LED. You'd run it through a pinhole. You can also just do this from a laser and get a much better result, in my opinion, a much easier result, in my opinion. But you're essentially imaging this point to your focus, that's providing your illumination, and then that point there, you're imaging back onto a detector. And you can do it in reflection mode as well. Oop. You can also add, so this gives you much better spatial resolution. You're starting to be able to get down to like the optical diffraction limit with this technique. You can also add dyes. So probably the single biggest use for confocal microscopes, I would argue, at least in research, is to do this with fluorescent dyes. So you take your thing like the cell that you want to image, you're going to stain the couple of different areas with some different fluorescent dyes, and then you're going to do some fluorescent imaging with this to get those out. All really cool. Okay, let's get a little bit more modern now. So what if we also did temporal focusing? So confocal microscopes are doing spatial focusing, right? We have 2 focuses, we put them on top of each other, and we take advantage of that overlap. What if we also did this kind of in time? So when we excite that fluorescence, right? We pump up some photons into this excited state, and after some time, they'll decay back down. After some time, there's this window in here where they stay in the excited state. And the cool thing is, if I come by and I get another photon to absorb before it drops back down, I can get a 2-photon absorption. And likewise, a 3rd photon, you can get a 3-photon, 4-photon, but it gets harder and harder and harder to do this. But I can imagine just looking at 2 photons. Now what we've done is we've created this kind of temporal dependence where we need to have a certain density of photons in a region and kind of almost like square that density requirement, and you sort of shrink your active area, your point spread function. And as you keep adding photon absorptions, you keep getting a smaller and smaller well-defined area. This is really, really, really cool for a variety of reasons. So first, it allows you to prevent absorption from surrounding tissue, Because if I come in here with something where I want to excite, for example, the 3-photon fluorescence, right? That means I'm coming in with, pretty long wavelength light that's not really going to necessarily get absorbed by everything around it. So I can get hyper specific contrast potentially to this dye that I might have added, or to some autofluorescence. But because it also requires this extremely precise overlap, I can also take advantage of the fact that this works really, really well in turbid media. So remember that turbid media, we want to go deep into tissue. This allows us to go really, really far into this kind of quasi-ballistic region. And one of the I would say the poster child from the community is these like rat brain images. So these will be 3-photon or 2-photon images looking into like a rat brain and going extremely, extremely deep, like 2, even 3 millimeters down. And they're able to resolve small structures like these neuronal cells down here. How? Magic. Multi-photon absorption, right? You can imagine by the time the light gets down here, it's basically not coherent. You just have diffuse light going all over the place. But because you're also imposing this extremely specific temporal overlap, and you're still kind of concentrating your photons, you can create these situations where you still kind of get focusing down there, even though this is well past the point where you'd be able to maintain a completely what's the term I'm looking for? Coherent. There you go. A completely coherent focus. So super, super, super cool. The only super resolution technique I'll talk about is STED, because it's the only one that I've bothered to understand that I also don't think is bullshit. You can take advantage of the fact that these fluorescent regions are not bound by your diffraction limit. So normally you're in any kind of optical imaging system, or in any imaging system, you're bound by a diffraction limit, right? Which is generally like lambda by 2. And the cool thing with this is you can get beyond that, because the actual excited region of the tissue, if I go in and I excite a bunch of electrons into a state where they're going to be fluorescing, there's nothing that says that that can't be very small. And so what you can do is you can go in and you can pump a bunch of regions like you normally would. And then you can come in with a ring beam, which is a thing that you can make. You can make a ring beam, and you deplete a bunch of these excited states so that you're left with a much smaller excited state. And then you let that state emiss back out, and you image that state. And this is really, really cool. Like, just like one example, you can literally search STED and find a million images like this. But comparing like a confocal microscope, which is already going to be operating like at the diffraction limit essentially, and you can just blow it out of the water with this type of technique. And basically anything that you can add fluorescent dyes to, you can get this down now to like tens of nanometer type resolution, whereas before you might have been limited to hundreds of nanometer resolution. So really, really, really cool. You can take advantage of other nonlinear effects. So we kind of already talked about multi-photon absorption, but you can also get second harmonic second harmonic imaging, where it looks very similar. You're absorbing 2 photons, but now it's the generated photon that elicits the effect. And you can use this as some contrast. Really, really cool. You can do fancier Jablonski diagrams, like simulated Raman scattering. You can take advantage of stimulated Raman scattering. Coherent anti-Stokes Raman scattering, CARS microscopy. You can also get some really, really, really cool endogenous contrast here. Insane. Absolutely insane. Okay, switch gears, talk about some photoacoustic imaging. So photoacoustics is a lot of my background, comes from grad school and so on. Photoacoustics is it's in the name, photoacoustic. You see with sounds. So you send in light. Usually you send the light in with a really short pulse, like a nanosecond pulse. And where that gets absorbed, that'll create a little temperature rise, creates a pressure rise, and then that sends out sound waves, like ultrasound sound waves. And so you can imagine these systems often just look like an ultrasound system that you've strapped a big laser to. And most grad systems look exactly like that and are exactly that. But these can also operate on a bunch of different resolution scales, all the way down from optical resolution, photoacoustic microscopy that you can still get to your optical diffraction limit, all the way to photoacoustic tomography systems, which are basically just those ultrasound systems, and get that same kind of 100 micron type resolution. In the optical regime, where you're still not going that deep and you're defined by that nice coherent optical focus, you can get really, really, really cool images. Like here's some made of mouse ear. Mouse ears are really nice because they're very thin and they got a lot of vasculature. You can see all this nice capillary networks and so on in a mouse ear. You can take advantage of that wavelength dependent absorption that we showed at the start to actually be able to map out blood oxygen saturation in these kind of structures as well. So for example, here's blood oxygen saturation in the iris of a mouse eye. It's really cool. You can also use color scale to kind of like map depth, these kind of things. And this is just cool because it kind of, like, this is done without any contrast. This is done like the animal is alive while you're doing this. You literally have a mouse. I've done these experiments. You literally have a mouse and you kind of like just put their ear with some water onto your like imaging surface, and you scan the mouse around for an hour to get an image like this. Really, really cool. But like you're leaving everything's intact. You're not doing any incisions. You're not adding any dyes, anything like that. At the extreme edge of this, we have photoacoustic remote sensing, or PARS, and this has probably demonstrated some of the coolest stuff in this field in terms of like microscopy for sure. So remember at the start of the lecture, I pointed out histology imaging and said that was probably the single most important thing that certainly probably microscopes are used for generally today outside of just research. This is aiming to replace that. So now all of a sudden you can get these pieces of tissue and using only endogenous contrast, mostly taking advantage of a combination of this photoacoustic effects and autofluorescence and so on. You can get at that same kind of contrast. You can see that cellular structure. Like for example, this is a piece of skin cancer on here. And there's no dyes or labels or added to this at all. It's just taking advantage of optical absorption and autofluorescence of UV specifically. So this is pumping at like 250 nanometers. And it's insane. And because you don't need to do any processing to the tissue, you can do this in tissue chunks. You can literally just take like a piece of tissue, like just a gray mass of amorphous tissue, and just slap it on the microscope. I'm not even exaggerating that much. And you can get image, like here's chunks of brain, like mouse brain. And you can see all these little dots. Those are cell nuclei. You can see the section of collagen and fibrin fibers that are like repairing. So this was a piece of skin cancer tissue that was removed, and you can actually see it try to start healing itself from the cut. You can see all these like healing mechanisms that the body would have initiated as you're doing the cut. In parts of again, more of this brain tissue, you actually see all this myelinated structures. So these are all the myelin, like neural connections and voids. You can see the difference between white and gray matter, and that's really, really, really cool. I could talk forever about this as well, but if you want to talk about later. On the other extreme side, how deep can you go? So this photoacoustic tomography, or PAT. these are the systems that look like just ultrasound systems, the big ass laser connected to them. And they don't just go through mouse ears. You can do whole hands if you have enough optic power and your acoustics are set up to detect them. So literally hold hands like this. This is a group out of the UK that makes these really nice acoustic resolution systems, and they got some nice processing too to get them beautiful. Probably the first commercial use of photoacoustic tomography is going to be in breast cancer as well. So this is a breast. Ooh, no. But basically what these systems look like is, you imagine you have a table with like a cup in them, and that cup is just full of water, and it's full of ultrasound transducers and like light pipes, and the patient can just lay down in there, and the breast hangs down in there, and they can just get full breast maps of the vasculature network. So if you have a tumor in here and you start getting dense vascular formation around that, like angiogenesis, that shows up in here. And it acts like a really good complementary, or I should say, it looks like it, because no one's quite done it commercially yet, but it looks like it provides a really, really nice augmentation to standard techniques where you're doing an X-ray. Because things like calcifications and so on will show up really good in an X-ray. But a lot of these soft tissue tumors don't show up in there, and they won't get caught until much later in their progression. So this type of technique looks super, super promising, and clearly not just for here. This is just the first application that's kind of coming out with it. Other cool stuff, and we're really reaching near the end here, I think, as well. We have optical coherence tomography, which, because of my current work, I won't touch this with a 20-foot pole, but it's really, really cool. The stuff I will chat about, probably the two biggest uses for it right now are in ophthalmology. So like looking at the retina. If you've ever been to get your eyes looked at, and if they suspect that they need to take a closer look at something like that, they probably put you on an OCT and looked at the back of your retina, your macula here. Because if you have any kind of detachments in your layers, will show up in here. You get these really nice volumes. The other big use for this is in endoscopy. Look, because you can make these into super, super small probes, and you can put them into blood vessels around the heart and so on, to take a look for ruptures, plaques, these kind of things. Really, really, really cool. Another cool technique that, man, it might be the future, but it's a tricky path, is diffuse optical tomography. So diffuse optical tomography says, man, I don't need coherent light. I don't need to use any kind of fancy acoustics. I'm just going to do the hard problem, and I'm going to solve, clearly not directly, but usually some kind of simplified version. I'm going to solve the radiative transfer equation. So this is basically the equation that describes how light propagates through turbid media. It's disgusting, but it's also extremely useful. So when you do this kind of diffuse optical imaging, you lose pretty much all of your spatial resolution. You're stuck to like tens of millimeter resolution with your optics, but now you can take advantage of optical contrast. So if you have different dyes or different things that have endogenous contrast, you can see these really clearly, right? And this is generally what's called something like a functional imaging modality, as opposed to like a something that gives you like a good picture. It's giving you functional information. It's saying, hey, there's a dense thing in whatever contrast you're using here, right? And if that was a dye that's connected to some kind of cancer marker, and maybe it's pooling around here because maybe there's a tumor here or something like that, right? Really, really cool. How this is generally done now is with radioactive elements, right? So if you ever heard of a PET scan or a SPECT scan, where this is basically what they're doing, but they're doing it with radioactive material, right? So they're taking a bunch of isotopes, they're labeling it with something that's going to be attracted to the thing they're looking at, like a specific cancer marker. Then they're going to inject that into your bloodstream. Now you're full of radioactive material. And then they put you in this kind of imaging chamber that detects where all these isotope decay elements are coming out, or neutrons are coming out, and rebuild structure to about the same kind of level of resolution. So you can imagine this offers a potential way of getting around that. Especially you can imagine if you're looking at, like a brain tumor or something near reproductive organs, or just organs in general that you don't want to just irradiate the crap out of. Offers a really, really cool potential alternative to that. Really, really cool. Polarization microscopy is really useful in especially like non-destructive testing. It also just makes really cool images. So remember at the start I said that you have the polarization state. That's basically just the orientation of the electric field, and in general, anything that you sort of interact that light with will be described by something called a Mueller matrix. This is the 4x4 matrix that describes how any given input polarization state gets kind of ejected back out. And if you can record that, which is actually non-trivial, these microscopes are super annoying to build. You can get really, really cool contrast that's giving you things like material stress. You can look at, for example, like how is, if I have a piece of metal, for example, like how is the stress distributed within this? Because the different regions of grain orientation and their density and so on will interact with the polarization in different ways. So it's also really cool for looking at like crystals and to shed light into their structure and these kind of things as well. Really, really fancy. You can do phase contrast microscopy, where now you're on the opposite side of like diffuse optical tomography, where you really care about the coherence, and now you're looking at the actual phase information of the light that comes back and imaging with that. This is super useful for finding extremely kind of subtle structures, especially in, for example, like biological samples and these kind of things. Really, really cool. The extreme of this is like quadrature microscopes, where a quadrature detector. Some of the electronics guys might kind of know like an electrical quadrature detector, like an in-phase and quadrature detector. This is just a optical version of that, which allows you to pick up the full phase and amplitude of light coming back, and you can get some really insane contrast from this. But these are absolutely awful to build, and they're still very much in research. Anyways, so in conclusion, optics is cool. Optics is expensive. I didn't really touch on this. Maybe I'll touch on this a bit tomorrow. Optics is like super expensive. I think that's part of the reason why it feels like a very unapproachable thing, is because it still is very unapproachable. Especially you start getting into custom optics and so on, you start looking at $700 for a single run of a lens, right? Like it's difficult to approach. So I think that was part of the motivation here, is to try to kind of get some exposure to some of these things. It's also very difficult. I think one of the other things I wanted to kind of just high level kind of describe is the fact that there's a lot of subtlety in absolutely everything going on here, and the level of complexity and thought and care that needs to be given to these devices to kind of get them to do anything other than be expensive pieces of metal and glass on your optics bench is pretty significant. Anyways, that was just high level primer. They're both inside the box. They can't hear me now. BTEX is a cutie. BT is a cutie. Anyways, big thanks to the DGen crew for letting me chat. And remember, this is meant to be a primer. If you have questions, please do ask. Well, probably Apple stepping in.
Hi.
Apple stepping in.
Clap. Yes.
Clap.
Yeah, we are still streaming, by the way. Clap. No,
Yeah.
thank you, Phil, for the lecture. Was great, actually, amazing. Okay, we're gonna do some Q&A now. We have like 25 people here, and also a couple of comments and questions on the stream on YouTube. So yeah, whoever has any questions, just let me know. We have a microphone here.
Here's a microphone.
Who has any questions?
Yeah, we can just form a line and then.
Oh yeah, Sky.
Oh, I think Schwann's.
Yeah, I think Schwann was trying to.
Anyway, I was just wondering. So you specifically talked about like a bunch of optical microscopy stuff here. Where does like the line between optical and non-optical microscopy end? Because like I understand that when you're talking, people talk about like electron microscopes, you're dealing with electron beams as opposed to these, which are not. But I don't quite understand where the line is.
Yeah. So again, I think I would describe the line in general as electromagnetic radiation. So clearly that would remove like matter waves, for example. Matter waves are really cool as well. But also, if you get long enough, you start to really it doesn't make sense to use optics anymore, and you start using, just antenna and these kind of things to start dealing with things. So I think it's kind of within that region, like I say, of where it still feels like optics, which feels like a cop-out answer, right? Like, but you're still managing your EM radiation with mirrors, with lenses, these types of things.
So you mentioned like the matter wave. So the electron microscopy is considered a matter wave, or am I confused or misunderstanding what you said?
Yeah, that's
interesting. Okay. Mm-hmm. All right, thank you.
All right, any other questions? John, yeah, you can grab the microphone.
Thank you again for the talk. Just a question for you. In terms of organic materials, are there any sort of organic materials that this would not be a good fit for?
Oh, I think for sure. I think in general, it's more so what is the most appropriate approach for the thing that you're trying to image or trying to detect, right? So I think in general, you can imagine that it's not so much that like one technique works or doesn't work. It's a matter of how well it works for the particular thing you're trying to look at. Like, for example, if I wanted to see blood vessel structures, the photoacoustics is really good for that, right? If I want to see, but I could still see the blood vessel structures with other approaches, like the OCT imaging, for example, has an angiography kind of mode that you can use to get those. Right, it's really more of a question of what is the thing that and maybe to that point, like if I wanted to look at a circuit board, I'm probably not going to use something fancy, like a photoacoustic system, right? So it's really, I think it's more of like what's more appropriate for the specific tasks that you're trying to do, the specific situation and contrast you're trying to take advantage of.
Understood. I guess what I was getting at more is like, is there any sort of organic material for which light would not be an appropriate tool? Like if any of these approaches would not be appropriate for?
If you need to go deep, anything that's really hard, right? Like if you can work in a reflection mode, then it doesn't really matter. There isn't really anything that's limited. If you have to work in some kind of transmission mode, then hard things like teeth or bone, for example, cartilage, these kind of things that the light just doesn't penetrate into. So those would be kind of those don't tend to work for most of these. Yeah.
All right. Thank you very much.
All right. So I'm sold. How much does the photoacoustic microscopes cost?
Which one? Like the photoacoustic tomography type thing?
The ones that you were looking at, like inside of animals. You said you could just sort of, you had a picture of a mouse's ear, that kind of stuff. Is that just in? You mentioned the cost of these things. Is this like a
So like say, for example, you want to build like a mouse scanner right now, right? The single most expensive thing is probably going to be your excitation laser in this case. So this type of thing, you'd probably be looking at like a nanosecond, like Nd:YAG with a second harmonic generator, fiber laser. You need pretty high rep rates for these because you imagine each one of these points is a single interrogation.
Every
So
pixel.
yeah. So you're probably looking at like, we'll talk brand new, off the shelf, not high volume or anything like that. You're looking at like 40, 50K USD for that type of thing. Then everything else, if you want a really good quality objective lens, a good quality objective lens can be 5 to 10,000. That works with the wavelengths that you care about. If these kind of things are stage scans, imagine all the optics are stationary and you're scanning the mouse around. So a good set of stages can easily be another 10 to 40K, right? So I think, like, all in all, a system that can do something like that without putting a lot of effort into cost reduction could be like 100K or so. A photoacoustic tomography system that can do more like this type of thing. A research ultrasound system that you don't have to, like, that's not too hard to pull apart, can be in the like 30, 40K. You can probably find a used nanosecond flash lamp laser, I don't know, for like 5K or so. So like that's, maybe you could probably hobble together something like this for like 30, 40K.
Okay, thank you. A bit out of my price range.
Hello?
Hello.
Hi, so it seems like photomicroscopy and photolithography have a lot in common.
Mm-hmm.
So how do those things relate, especially in terms of our current situation of having trillions of dollars going into chip development? I mean, is that having a positive impact in your field? And how do you think the advances in chip development will affect microscopy and vice versa?
I think to answer maybe the second half of your question first, I think specifically for optical imaging, most inspection done by modern litho is usually like E-beam. Like it's just electron microscopes at this point because the structures are just too small to realistically be productively imaged by a lot of these techniques. Though there is some non-destructive testing, again with things like the polarization microscopy, because it can see things like stresses and so on. So imagine you have a big wafer and you put a couple hundred layers on there, and maybe you want to image how that's stressed or so on. So that something like polarization microscopy offers a potential avenue into doing that kind of like non-destructive testing. So I think I would say, if anything, they're sort of drifting apart, those two kind of techniques. In terms of like lithography is just like the inverse of an imaging system, essentially, right? In lithography, you start with a light source, you focus it down onto a thing. In at least like a regular microscope, you're looking at a thing and focusing it back onto a sensor. Some systems, for example, like those confocal systems, remember, where you have the light source and you're focusing it down onto the sample, right? That's a lithography. If you just cut off the right side of this is a lithography system, right? Just a light source that's focusing some sort of defined structure, like a point source, down onto the sample for a simple like single point.
Okay, so I guess a follow-up question. Modern lithography is using extreme ultraviolet. Is that becoming a thing for optical microscopy?
As far as I know of, no. I think that something like EUV imaging, I feel like it's this weird nexus of it's probably not going to be better for imaging than something like E-beam, sorry, I keep saying E-beam, but better than like electron microscopes. and it has the double kind of negative that it's extremely expensive. Like the way that these coherent extreme UV systems make that extreme UV light is extremely expensive. Like you're blasting like little balls of I think tin or something like that to create these like coherent X-rays. It's not something that's going to be very practical for imaging. It's going to be insanely cost prohibitive, and I think for no benefit above something like a electron microscope.
Okay, and then I guess my last question, in the current market, is microscopy benefiting from the massive investment that's being poured into chip development, or do you think it's
I don't
attracting
think so.
investment away from it?
I don't know about attracting investment away from it. I think that's a really hard question to try to answer. I think that I feel like a lot of the modern development, like the techniques that they would be using, like standard inspection microscopes and so on, this is old technology. This is stuff that's been around for 100 years. They're not, again, outside of maybe some hyper-specific like non-destructive testing scenarios, they're probably, I can't imagine that they're touching a lot of more modern techniques. A lot of the more modern imaging techniques seem to really be looking at like that's not destructive, that's not non-destructive testing, is a lot in biology, right? And so they're kind of diverging away from each other, I would say. But taking money away, I mean, in a zero-sum game, I guess they're taking money away in that sense. But I feel like they're two separate sort of.
Cool.
entities.
Thanks so much.
Yeah.
I had a question. One of your slides, you mentioned ramen.
Yeah.
Can you go to that slide
made
real
you
quick?
hungry?
So yeah, yes, it literally is that silly. I had this moment where I was like, "Is he just making up words right now?" Yeah, okay. And I was curious to know, like, how do you spell it? I assume it's not actually ramen.
Oh, Raman. It's a guy's name. It's like a guy's last name. I think
Oh,
I think
okay.
it's the same
Close.
spelling. I think it's the same spelling, isn't it? Or is it very similar? But it's a guy's name. It's not.
Okay.
It's got,
All right.
it's got an
So
E,
so
not
we
E.
Yeah.
instead of an E, right?
It's like
And then
Raman.
what did you call these diagrams?
Jablonski diagrams.
That's a great name.
That also sounds like a. It sounds like.
Fantastic.
It sounds like another way to put. I love it though. I love it. Okay, it's
They're
because it sounded like Jablinski, and that's like I don't know. It's like a made up person's name that I've heard before. And it's like, okay, yeah, the Jablinski diagrams and you know, Mr. Ramen, yeah, okay, guy. But no, I get it. I know it's real. But
yeah, these diagrams are really actually cool for just like extremely what do you call it, like abstracting away energy levels, like especially like electron energy levels, where if you just like you throw away literally all of the complicated physics and chemistry that's like actually going on, and you just say, well, what if I just have some lines on the paper basically that represents my discrete energy levels that my electrons want to exist at, and then because then it makes it really easy to think about things like you know, so like Raman scattering, for example, is just you basically emit down to an energy level that you didn't start in. So for example, I emit a longer photon than I pumped it with, right? So these kind of diagrams just make it really convenient to sort of express those ideas.
cool. Thank you for explaining that.
Yeah,
You put a polarizing filter in front of them. It's quite that simple. Like if I go back to my polarization diagram, you imagine I have a camera sensor that's behind a polarization filter. And that polarization filter doesn't have to be a linear polarizer. It could also be like a quarter wave plate with mixed, or a half wave plate mixed with linear polarizers if I want to be able to detect. This is also not a made up term. This is the proper term. Detect the retardance of the light, right? Essentially, like how much uneven phase accumulation do I get? How much delay in phase do I get between my major and minor axes? So like how much ellipticity or how much circularization do I get from a polarization? But quite literally, that's how it's done. So you imagine like a full Mueller matrix polarization microscope where you're trying to detect this like 4x4 Mueller matrix per location. Remember, per location, like per pixel on your thing. You usually have some kind of switching system where you're switching different polarization plates in and out of your system and taking 16 images and then reconstructing those.
Okay, thank you. Another question is, how common is hyperspectral imaging in microscopy?
How common is it?
Yep.
So I think generally, first let's be careful. So hyperspectral imaging, I think generally refers to like an endogenous like scattering or transmission in there, and I would argue that that's reasonably common. I think a more common use, I think it depends how you define hyperspectral, right? So like for example, there's nothing saying that I'm trying to think of some good examples, because certainly there are a lot of microscope systems out there that, for example, will take advantage of more than one type of the contrast or one kind of color, as it were. I think my response to that is I don't think it's particularly common, but there's certainly good use cases out there, and I think in the same sense of more conventional hyperspectral imaging, right? Sometimes you have a highly multiplexed system that you want to collect these, we call this like 4 or more different data channels. But I think those are more relegated to a specific application as opposed to relegated to a specific modality.
Okay, great. We have one more question on YouTube. This is more in the basics area. You can just explain a bit the difference. Interesting how the lens acts like a parabolic object that directs all the rays into a focal point. Yeah. Does that mean satellite dishes can be a form of EM receiver a lot like an eye? So basically, the guy is asking if you can you can make like a reflecting optical system. Yes.
Yeah, of course. Yeah, and there's even good use cases why you would want to do that if you're using. So remember, we talked about there's this like kind of like this dispersion effect, right? So you get different behavior. Well, the slides are taking a while, but you have different behavior of light for different wavelengths. If you go to extremely short, I guess this is the right slide for this part. If you go to extremely short pulses, like especially single femtoseconds, you can imagine that the femtosecond pulse is not a single wavelength. It's a very wide band source. It's a big spread of wavelengths. And so if you want to simplify your life a lot, you can switch to just an all reflective system, right? And a lot of really, really short pulse systems do this, right? You start throwing away lenses because lens design becomes extremely difficult at these kind of time scales, and you just switch to mirrors. Mirrors still impart some dispersion, but it's easier to control, and it's a lot less than you get from a piece of glass. So yes, in broadband systems, so systems that use a lot of different wavelengths, reflective architectures are pretty common. In general, they're a lot cheaper to make as well. They're just bigger. It's very challenging to make an all reflective system miniaturized.
Okay, thank you. Yeah, let's keep going with the questions here. So, Alex.
Thank you.
Yeah.
Yeah, I have a question that I always wondered about lenses and mirrors.
Mm-hmm.
How light interacts with the material at an atomic level versus at a macro level. Because at a macro level, you can see a lens or a mirror with like a slight curvature. But at an atomic level, if it's made out of a, say, a crystal, wouldn't it just be like layers of atoms going in sort of like a stair step, sort of like a Minecraft surface? And if so, why doesn't the light just bounce off at the same angle everywhere? Do you understand what I mean?
Yeah, I get what you mean. I think that I think the way to think about that is if you treat your light as this wave structure, right? That it sort of acts like a masking for things that are much smaller than the wavelength, right? So if you start talking about molecules and like this kind of size or right, that's much smaller than the wavelength of the light that's interacting with it.
Right.
So for example, like if you somehow could send like a non-quantum photon in there or something, right? Like and I think you're on the right track, right? It's interacting with, you have a single photon that's collapsed and it's interacting with a single molecule kind of thing. But when you have this whole wave kind of pumping through there, it's not seeing that scale, I guess, is a way to think about it. It's not interacting with that scale in a way that isn't just like a bulk interaction.
Okay.
Right.
Okay.
Like you're still getting individual photons interacting with individual molecules and scattering off of these, but like the bulk behavior is just kind of immune to that scale.
Okay, so it's a factor, but it's so minuscule that is you can.
Yeah, I would say it's a factor if you care about the material specific like physics of the interaction for some reason, like for a particular experiment. But for example, it would never be something that you would consider in like an optical design, for example. Optical design, you're going to concern about like the flatness or the how good of a form you have on your lens and these types of things, but you're not, for example, taking into account that nanometer scale jaggedness that it might have, for example.
Right. Okay. Yeah, and a second question regarding lithography. Because I've seen that they're now making like ultra what was it called? The NA, the NA,
extreme,
like
extreme ultraviolet.
No, not it's like something with the NA, something with the lenses
aperture.
and the mirror. Yes. So, do you think that we're at the limit of like lithography? Or is like Moore's law gonna keep going in some other fashion, or is it like tapped out at this point?
I think honestly, I think that Moore's law has been dead for a while, but I don't think it has anything to do with lithography techniques. I think it's more to do with just you can't make a transistor that's like realistically, I know there is papers out there that have like single molecule transistors and stuff like that, but you can't functionally make a transistor at that type of scale. So I feel like the bigger limitation is how small a transistor can be, as opposed to how small of a transistor can we make. Yeah.
Okay. Yeah. All right.
Yeah.
Well, thank you.
Yeah.
What kind of material limitations do you face with modern day optical things? Like if you had a magic material in your lab what would it be? Would it be like a lens or like a pump or a lasing crystal, and like what problem would it be fixing?
So I think the magic material would be something that doesn't have dispersion, right? So that the presentation's just completely frozen now. But remember, so again, going back to that wavelength dependent refractive index, that is what makes optics hard. That is what makes optics hard. So if you had a material that has no dispersion or at the very least extremely negligible dispersion, that would be pretty magical. I think also material that has really good shortwave transmission. So even working in regular UV, not extreme UV, but regular UV in like the 200s kind of range, you very quickly run out of materials. Like in terms of common materials out there, you have like calcium fluoride and UV fused silica, and they realistically only kind of go down to like 190 or so. And even at those things, they solarize, so the UV still actually damages the material, especially at high energy densities. So it's extremely expensive and limiting to try to work down there, which is a shame because there's a lot of really cool stuff that you can do with UV light that just makes it, it's the same problem of unaffordability and complexity, but it's just adding on to the pile kind of thing if you're also trying to work in UV. So yeah, I think it's dispersion, no dispersion material, something that works better in UV, I think would be some magic materials.
Thanks.
Okay, do we have any other questions? Or,
Nope. Oh, excuse me. So what are some of those physical interactions that can cause changes in, say, like a lens substrate with UV versus other wavelengths of light? Because
I'm actually I'm not too sure of the exact mechanism. So this process, at least with UV and supposedly UV transmitted materials, is generally called solarization. Like think sun, like solarization, and it at least displays itself as the material's transmission gets worse over time and use, to the point where a lot of UV lenses, especially that are in high intensity, and keep in mind, I'll also preface, this is a different ballgame than extreme UV. Extreme UV is a different thing. They do different things with their optics. This is not that. But in like regular UV town, a lot of times like lenses and stuff are just consumable. Like just straight up, if I buy a high power UV laser, a lot of the lens modules in there are designed to be removable. They'll have like a 2,000 hour shelf life, and then you swap them, right? Like, so this is a real problem in this kind of regime. The actual mechanism, I don't actually know the details of it, but in general, the issue with UV is just it starts to gain the ability to ionize and denature things, right? So high energy photons having the ability to gradually break away at, I don't know, probably defects.
What
and
kind
so
of
material.
What kind of materials do you use for lenses in your area of specialty? I mean, it can't just be regular old melted sand, right?
No, that's right. So it'll be melted sand, but usually with different dopants and so on. So different additives in there to get different dispersion properties, to get different cost, hardness properties, and these kind of things. Could have actually been a good thing to include here. You can also look up, if you search like Corning or Schott, their glass tables. That's kind of like a titular tool in the optic designer toolbox. There's, I think, like almost 1,000 or so quote unquote commonly produced optic glasses. more common, like common are probably more of a family of like 50 or so. But they really are just basic glass, just with different dopants and done to a much higher level of purity than for example like window glass would be.
Final question, and I think it's a question of opinion. Is glass a slow-moving liquid, or is it a solid with liquid characteristics?
I think for my purposes, I would consider it a solid because I can treat it like a solid. I don't know. I would say in my experience, I don't think I've ever seen the glass drooping on a realistic time frame for the life of these kind of instruments. So I would say I'm going to put my hat into the solid bin for this. But
All right.
Okay, I think that's it.
hooray!
Okay. 1 second. Yep.
We clap.
Clap. Okay, thank you, Fizz, for the lecture, for the Q&A. Actually, we had a lot of questions, and that just shows that okay, people are actually really interested in this. And I think it was a very good lecture. Okay, if you want more of this, join the Discord server, join the group. We are streaming a lot, and we are doing casual events like once a week or more. We're also doing chess on Sundays, and yeah, join the Discord, join the events, join on VRChat, subscribe to the YouTube channel. Yeah. Now we're gonna go to a casual event. We're gonna do a casual instance. And,
what is this? What group is this?
oh, this is DT Tech. Yes. Okay, DT. Yeah, you do it. You come, DT. DT is our new host. It's one of our new hosts, and yeah, he can talk. He can talk better than me, probably.
I don't know if I'd go that far, but wanted to say, thank you again for the lovely Physwolf for the lecture. For anyone who may have joined the live stream a little late, this group is DGen Tech. We are a group of furries in the science, technology, engineering, medical, and mathematics fields. We have a YouTube, which is where this stream is being hosted at. We have a Discord. If you're interested in the community, hit us up on VRChat or Discord. And that concludes the formal part of this lecture. Have a good night, everyone.